Okay, this is week 4 in another tutorial looking at another algorithm. If you go to the home page and tutorials for week 4, we're going to talk about the merge sort. So the merge sort, well, I'm going to go through this relatively quickly. The merge sort is an algorithm that is popular. It's a classic. It's one of the ones you need to understand how it works. And it's just a classic, simple algorithm that performs a very common piece of work. And of course, we're going to end by evaluating the efficiency of it. Now, I went through an explicit example of this in class, so I'm going to go through this relatively quickly. This is a slightly simpler example in class, but it comes up with a bit of a twist compared to the example I did in class, so maybe it will answer some confusion. So I am going to go through it, even though I did go through an example in the lecture video. So the idea here is to take a sorting task with a big array and to break the problem of sorting down into smaller bits of problems one at a time. So we take the whole array, cut it in half, and we focus on one half at a time. If it's still long, we cut it in half again until we get a small chunk. And when we get a small chunk, we're going to sort the subsets of the chunk and merge them together so that they are in order, the smaller chunks. And for a real long vector, we may have to do that quite a lot of times. All right. So in this algorithm, this is one of the classic way to implement this has a recursive element where when we merge, we're going to use that merge at every step depending on how many levels we need to do. So we're going to do the same steps over and over again recursively, right? So in pseudocode, we're going to start with an array, and we're going to sort the left half of the array, assuming that there's more than one element in the array. We're going to then sort the right half of the array, assuming there's more than one element, and then we're going to merge the two halves together, okay? And we're going to do that iteratively for an array. So we're going to start with an array. Now the twist on this is the example I gave in class had an even number. So we always had a perfect division. And this is going to result in the first one. The first split's going to have an odd number. And what do we do then? It's actually even simpler. So we're going to follow our pseudocode. The first thing we're going to do is to cut the array in half and sort the left half. Okay. So we're going to ignore this half at first. And, well, this is interesting because now we have to cut it in half. What do we do? Well, we'd have to specify how we're going to cut it in half if there's an odd number of elements, right? So in this case, what we're going to do is cut it in half, airing to the left here. And in this case, we end up with just one element, which we bring down. Because there's only one element, it's already sorted this half. So this is the second pass we've done for the half. Let me just back up and make sure I underline that. First, we've cut the whole array in half, and now we've cut this subarray in half again. So we sort the left half of the array. It's already sorted. Now we sort the right half of the subarray. So this is 2 and 1. We bring down the 2, bring down the 1. We ask, are they sorted? Heck no, they're not. So we're going to sort the right half of the array. Now we've got the two halves of the array. We're going to merge them. And remember, it's the two-finger technique. Our left finger's on the first element of the left side of the array, and our right finger's on the first element of the right side of the array. So we compare 5 to 1. And we take the smaller one and put it on the left. That's 1. Now our left finger's on 5. Our right finger's on 2. We take the smaller one and we put it in the next position. That's 2. And there's only one left. So we put it in 5. And now our left half of the whole array is sorted. So now we're going to do the right side of the array. So we've clicked back up. We've done this for the whole array, and we've done it for the subset of the left half of the array. And now we're going back up to the right subset of the whole array. So we're going to do exactly the same thing. We're going to consider the left half first, bring it down. It's only a single number, so it's already sorted. We're going to ask, are those sorted? They're not. So we're going to bring the numbers down and then sort them. Again, we can think of this as the left and right finger method. Left finger on 6, right finger on 4. Which one's smaller? 4, of course. We bring it to the next position. So now we've got the right half of this subarray sorted, and we have to merge them. So we consider all of them. Left finger on 3, right finger on 4. Are they in order? Yes, they are. We bring down the 3. And then we bring down the other 2 because they are already sorted as well. All right, so now what have we got? We've got our sorted left half of the whole array, our sorted right half of the whole array. We're going to merge the 2 together. Left finger on 1, right finger on 3, which is smaller? 1, we bring down the 1. Left finger on 2, right finger on 3, which one's smaller? We bring down the 2. Left finger on 5, right finger on 3, which one's smaller? We bring down the 3. And so forth until we're sorted. And we've merged now the 2 halves together. And once we finish that, given the length of the array, we may have to go very many more levels if it was a really big array. We're finished. Now the worst case scenario is that we have to split up in elements and recombine them. And it doubles the sorted subarrays as we build them up, but each of the subarrays is smaller as we split them in half. So we, in other words, combine the sorted 1 and 2 element arrays for the case we have an odd number at the very smallest level, and we combine sorted 2 element arrays into 4 element arrays, and so on and so on and so on. Best case scenario is our array is already perfectly sorted. We actually still have to split them up and combine them by this algorithm in that way. I mean, we could talk about it in the notes a little bit. We could do a check, a dummy check in this algorithm to mitigate this. But without that dummy check, the best case scenario is we still have to go through them. So, of course, we're thinking of omega and big O here. And because of just the native simplest form of the array doesn't have the dummy check, let's just pretend that we're not doing that, which would be rare. It'd be very rare anyway, and therefore it's probably insignificant. So the efficiency here is a log value. It's n times log n. So it's not very efficient to do this. If we think about the linear sort kind of thing, and remember it's not that efficient, and omega is the same because we have to go through it again. So that's how we think about it. That's merge sort, and that's all I have to say about that.